Hello, welcome back to the Garage Lab. So excited that you are here today. We're going to take a brief moment to kind of pause our normal discussions to kind of brain dump some pretty important information. If you take one thing away from our chemistry discussions, I hope it is this tidbit, this piece that we're going to talk about here for the next 4 minutes. Because everything in chemistry has to do with electrons. Whether you react with something, whether you are stable, what kind of light you give off, how much energy you have, what element you are, not really that last one, but all of it has to do with how many electrons you have and the way your electrons are configured around your nucleus. And our big takeaway here is that every single element on the periodic table, whether you are hydrogen or lithium or beryllium, every single element wants to have 8 electrons in its outer ring, which sounds a little bit crazy, but just bear with me for a second. I'd like to show you this guy. If we were looking at this picture here, a scientist should jump into your brain, somebody who we talked about very, very briefly. You should be like, oh yeah, I saw that. Who are you thinking of? You're right, you're thinking of Niels Bohr, right? The Bohr model of the atom with these electron rings, right? He's like, this is the ladder model. Electrons live on the rings, but they can't live in between the rings. They can jump in between, but not in between. They can jump from rung to rung, but they can't live in that empty in-between space. That's what we talked about. Well, we're gonna kind of revert back to that model of the atom. So I'm showing you a model of the atom here. This is a positively charged nucleus, and this positively charged nucleus is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. Look at your periodic table. What element are we looking at right now? It's a neutral atom. 11 electrons. It's in, we haven't talked about groups yet, we're talking about that next. It's towards the left of the periodic table. You're right, it's sodium. We're looking at sodium here. We can tell that this is sodium because it has 11 electrons, and sodium is atomic number 11, meaning that the number of protons and electrons here are equal. What we're looking at here is a couple different rings. These electrons are living on these particular electron levels. This one electron here is living on this outermost ring. These 8 electrons are living in the innermost ring, and these 2 electrons are living in the innermost ring. Magic number for us here today is 8. This sodium atom, in order to be happy, wants to have 8 electrons on its outermost shell. And right now, his outermost shell only has 1 electron. So what this sodium atom is going to try to do is one of 2 things. He has 2 options. Option 1 is to get 7 more electrons in order to fill out this outer shell and reach magic number 8. Option number 2 for the sodium is just to get rid of this 1 electron. And if he gets rid of this 1 electron, he'll have 1, 2, 3, 4, 5, 6, 7, 8 electrons on that outermost shell. If the shell has no electrons on it, it doesn't count anymore. It kind of gets erased. So if we get rid of this 1, we're already at 8. What's the sodium gonna do? Gain 7 or lose 1? You're right, it's super easy to lose 1 electron instead of gaining 7. Imagine walking up to your buddy and being like, hey, give me $1. He's like, yeah, sure, no big deal. I'll give you $1. Imagine walking up to your buddy and being like, give me $7. Right? Your buddy's gonna be like, no, I'm not gonna give you $7. I'll give you 1, I won't give you 7. Right? These elements are gonna take the path of least resistance, which in this case is just getting rid of 1 electron. So what this sodium atom wants to do is get rid of this 1 guy. In order to have a full 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons on its outermost shell. Sodium is happy. It has reached a magical number 8. You're with me so far? Good. You guys are so smart. Let's take a look at some other elements here for just a minute. We're going to look at an element on the further side of the periodic table. So we're again going to have a positively charged nucleus. Let's look at fluorine. Fluorine is a nonmetal, so it's on the right-hand side of the periodic table. its atomic number is 9. How many electrons is fluorine going to have? You're right, it's gonna have 9. It's kind of hard to count and like do this at the same time. All right, so here's what our fluorine is tentatively gonna look like. For right now, it's not important that we can draw these ourselves. We're gonna do like a lot of this. So for right now, we just wanna feel comfortable with this idea of every element wanting to get to the magical number 8. Right now here's fluorine. He's got 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. In order to get to that magical number 8 though, on this outermost shell, what does this fluorine need to do? How many does he have, first of all, on this outermost shell? Right now this fluorine's got 1, 2, 3, 4, 5, 6, 7 valence electrons. We're gonna call these guys here, these electrons on this outermost shell, valence electrons, which is sometimes hard for me to say. It's spelled with a V. I am gonna tell you that for the rest of our lives, because I am the laziest chemist in all the land, I'm gonna abbreviate valence electrons as V and then our cool little electron symbol. So right now this fluorine here has 7 valence electrons and he wants 8. Just like sodium earlier, he's got 2 choices. Option number 1, he can get rid of all 7 of these electrons and then have a full outer shell. It would only have 2, but it's okay, don't worry about it. He can get rid of these 7, or he could just gain 1 electron. What's easier, getting rid of 7 or gaining 1? Gaining 1! So what this fluorine is gonna do is it's gonna steal an electron from somewhere else in order to get that full magical 8 electrons on that valence shell. We're gonna say that the easier it is for something to reach 8 valence electrons, the more reactive it is. So these elements that have a lot of valence electrons, like 7 or 6, are very, very reactive because it's very easy to get 2 or 1 electron. Conversely, on the other side of those periodic tables, elements with very few valence electrons, like 1 valence electron or 2 valence electrons, are also going to be super reactive because it's really easy to get rid of 1 or 2 electrons. Elements in the middle that have 3 or 4 or 5 valence electrons are going to be less reactive because it's harder for them to reach that magical number of 8 valence electrons on their outer shell. Just keep this in the back of your mind as we move forward here. Few valence electrons, super reactive. A lot of valence electrons, super reactive. Middle range number of valence electrons, not really reactive. We'll discuss it more in general, we'll discuss it more specifically as we move forward, but for right now, just in general, we want to have this idea of everything wanting to get to 8. It's going to help our discussion that you're going to watch here in the next couple minutes. Okay, if you got some questions, hop on the Google or the Zoom and let me know. Other than that, I miss you terribly. And you're moving right into the next video. So see you in like 35 seconds.